Hi, my name is Steve Blyle and I'm a welder. Both for its speed and ease of operation, wire feed has become the standard in the welding industry. And with the availability of smaller diameter wires and less expensive welding machines, semi-automatic wire feed processes are now common in smaller shops, on farms, ranches, and even in home shops. Today we're going to look at flux core arc welding. This process uses a continuous tubular wire that surrounds an inner core of flux. Compounds added to this flux determine the characteristics of the arc and weld buildup. During the weld, these compounds clean oxides from the surface of the metal, helping the molten puddle to flow out. They also lift oxygen, nitrogen, and other impurities from the molten filler metal, producing a clean weld deposit. As the molten flux cools, it forms a protective slag covering over the hot weld bead. Now, in any type of welding, the molten metal needs to be shielded so that it doesn't come in contact with oxygen and nitrogen in the surrounding air. Flux core arc welding shields the molten metal two different ways, depending on the type of flux core wire, self-shielded or gas-shielded, and these really are like two different processes. With the self-shielding wires, the molten weld puddle is shielded by gases created from the burning flux. These wires typically require less voltage, can be used over a wide range of metal thicknesses, and deliver a moderate deposit rate. Self-shielded flux core wires provide a wire feed process that's relatively mobile and can be used outside of a shop for structural, general fabrication, and repair. Self-shielded flux core wires are extremely versatile, and for beginners, it's probably the easiest type of welding to learn and use. With gas-shielded flux core wires, the compounds in the flux do not produce the gases necessary to protect the molten metal from contacting the surrounding air, so an externally furnished shielding gas is needed. These wires generally require a higher voltage, are considered most efficient on thicker metals, and provide high deposit rates. Because of the external shielding gas, these wires are used inside of a shop or some confined area for heavy fabrication and equipment repair. Both self-shielding and gas-shielding wires have the potential to produce strong welds. There are differences between the two, both in setup and welding techniques. So let's start with self-shielded flux core arc welding. Self-shielded flux core wires were originally developed as an alternative to shielded metal arc welding, which is stick rod. With higher deposit rates, wire feed is more efficient. It's also easier to use, especially for beginners. In electric arc welding, the distance between the electrode and the metal, called the arc gap, is extremely important. Any change in the length of the arc will affect the amount of heat at the weld. With the wire feed processes, when the voltage and wire speed are set properly, the welding machine automatically maintains a uniform arc, even with slight variations in the position of the wire feed gun. You can run a weld bead the very first time you pull the trigger, but there is a little more to joining metal than just squirting wire. While the equipment does feed wire and maintain the arc, the welder still needs to control the position of the wire feed gun, the direction of travel, and the travel speed. There's also metal preparation and joint fit-up. To use wire feed effectively requires the physical ability to control the wire feed gun, along with a basic understanding of the equipment and welding wires. A standard setup for the self-shielded flux core wires consists of a power source, a wire feed unit, the gun assembly, and a ground clamp. Smaller wire feed machines up to 200 amps will generally have the power source and wire feed unit combined. In the welding industry, where more powerful equipment is used, the wire feed unit may be separate from the power source. Wire feed welding machines may look different depending on the size and brand name, but they all do the same thing: feed wire and regulate current. So basically, they all have the same parts. Self-shielded flux core wires are typically used with a constant voltage direct current power source. Alternating current from the wall outlet is transformed into direct current to the electrode, which is the welding wire. The direction of flow, referred to as polarity, is determined by how the leads are connected to the terminals on the welding machine. For direct current electrode negative, or DC minus, the lead to the wire feed gun is attached to the negative terminal and the ground clamp is attached to the positive. In theory, negative electrons flow from the welding wire, striking the base metal and forming the molten puddle quickly. Electrode negative is generally associated with lower voltage requirements and faster travel speeds. With direct current electrode positive, or DC+, the lead to the wire feed gun is attached to the positive terminal and the ground to the negative. Current flows from the metal to the wire. The molten weld puddle is formed by hot gases surrounding the arc. Electrode positive generally requires higher voltage settings and slower travel speeds. Self-shielded flux core wires are developed to run on a specific polarity. Some use electrode negative, others use electrode positive. It is important to set up the equipment for the polarity of the wire you're using. Wire feed also uses a constant voltage power source. This is different from a stick rod welding machine, which uses a constant current power source. During the weld, either the voltage or the amperage is always changing to maintain the arc. In wire feed welding, this mainly happens when the gun is held closer or further from the metal. With CV power sources, the voltage is set while the amperage varies to provide the current necessary to burn off the wire and maintain the arc. Constant voltage power sources stabilize quickly, maintaining a uniform arc length and allowing the drive rolls to feed the wire at a constant speed. In some situations, a constant current power source can be used, along with a voltage sensing wire feed unit. With the constant current power source, the amperage is set and remains fairly constant, while the voltage varies to maintain the arc. Special wire feeder units, often referred to as suitcase models, are designed to sense the voltage changes and vary the wire speed to maintain a uniform arc length. Voltage sensing wire feed units are typically used and work best with bigger welding machines and larger diameter wires. The wire feeder unit itself, either constant speed or voltage sensing, is fairly simple. There's a spindle to hold a roll of wire with a catch that's inserted into a hole in the back of the spool. The spring-loaded nut at the end of the spindle should be tightened just enough so the spool stops when the drive rolls stop and it doesn't continue from momentum. Drive rolls are designed to match the diameter of the wire indicated on the side of the rolls. The gun assembly contains a liner for the welding wire, a lead supplying current to the contact tip, and control wires attached to the gun trigger. At the end of the gun, there's an adapter, the contact tip, and a thread cover to protect the threads on the adapter. The contact tip is the last part of the welding machine's electrical system that energizes the wire. Tips are available with different size openings, and for good contact, you want the tip to match the diameter of the wire. To load the wire, mount the roll so the wire comes off relatively straight through a guide that keeps it centered in the groove on the drive rolls and into a steel liner inside the gun assembly. Before you close the drive rolls, make sure the wire is centered on the groove, then tighten just enough to keep the wire from slipping. Flux cord wires, which are relatively soft, can be deformed if the drive rolls are over-tightened. With the spool loaded, lower the hood, turn the machine on, straighten the lead up a little and pull the trigger. There is a very close tolerance between the opening in the contact tip and the wire diameter. You may want the contact tip removed until the wire is all the way through, then reinstall it and you're ready to weld. Now, part of wire feed welding is maintaining the equipment to keep the wire feeding smoothly. It is very difficult to make a good weld when the wire is coming out in spurts, so let's look at a few things you need to pay attention to. Even though the wire looks clean, it does cause dust from the shop to gum up the liner. Installing a wiper with solvent made especially for welding wire helps keep everything operating smoothly. During the weld, small bits of hot metal called weld spatter fly out of the molten puddle. Depending on how clean the metal is and the position of the weld, globs of spatter may stick to the end of the contact tip. Occasionally, check the tip and scrape off any buildup. The wire can also burn back and stick at the tip, so it's a good idea to keep a few extra contact tips on hand. Wire feed machines are well built, and in most cases, feeding problems are not equipment failure, but rather some kind of contamination, either dust from the shop or weld spatter. Take the time to keep the machine clean and the wire feeding smoothly. Since the 1980s, when self-shielded flux core became popular, new wires have been developed to make this process more versatile and easier to use. Welding wires are classified by the properties of the finished weld. The E stands for electrode. The 7 indicates the weld metal has a 70,000 pound per square inch tensile strength, and tensile strength is the force it takes to pull it apart. The 1 indicates the wire can be used for welding in all positions: flat, horizontal, vertical, and overhead. A 0, like an E70T4, means the wire was designed for welding in the flat position only, or for a horizontal fillet. The T stands for tubular, indicating it is a cored wire. The last number refers to the characteristics of the arc and the properties of the weld. Depending on the type of flux, self-shielded wires can provide deep penetration or build up more weld. Some are limited to single pass only, others can be multi-pass for larger welds. Keep in mind, most wires were developed for industry, where welds are often made in the same position or specific mechanical properties are required. E70T3 and T10 are high-speed single-pass wires. E70T4 and T7 are multi-pass wires with high deposit rates. E70T6 and E71T8 are multi-pass, deep penetrating wires that meet the impact requirements for welding structural steel in seismic zones. For general purpose fabrication and repair in all positions, E71TGS is often used with the lower voltage hobbyist type wire feed machines. These are recommended for a single pass weld with limits on the amount of weld buildup. E71T11, one of the most commonly used self-shielded wires, can be multi-passed, but is often limited to a weld buildup of 3/4 of an inch. With a smooth arc and spray metal transfer, E71T11 wires provide good weld fusion and are very easy to use in any welding position. This is the type of self-shielded wire we'll be using for our demonstrations. The diameter of the wire is selected for the amount of filler metal deposit, and in some cases, the size of the welding machine. In the welding industry, larger diameter wires provide maximum weld deposits in the flat position. Smaller wires are used for vertical and overhead welds, depending on the thickness of the metal. For general purpose welding, where you're working with different metal thicknesses in different welding positions, it's more of a compromise. 030 works well for the thinner gauge metals. 035 is used when the metal is mainly 1/4 of an inch or less, and both of these are commonly used with the smaller wire feed machines. 045 and larger wires are used for metal that's 1/4 of an inch and thicker. These are generalizations. If you can handle more metal, try a larger diameter wire. If you're doing a lot of vertical and overhead, you can always use a smaller wire for less weld deposit and better control. One last thing about flux core wires. These are classified by the finish weld, and the way manufacturers achieve this varies. Some wires, even in the same classification, may be easier to use than others. If you seem to be having a problem, you may want to try a different brand of wire. Okay, we've set this machine up with E71T11 all-position self-shielded flux core wire. Let's try some welding. Before you pull the trigger and throw sparks all over the place, cover yourself up. Wear some good gloves, a hat, and always wear safety glasses. Along with hot metal sparks flying around, slag or other impurities can pop from the surface of the metal as it's heating up or cooling. Make sure the lenses in your welding hood are clean. Use clear lenses to protect the shaded lens and check that everything is sealed so light doesn't leak around the edges inside the hood. Keep your work area clean and always have a fire extinguisher handy. Ideally, the ground clamp should be attached as close as possible to the weld. That's not always practical. Sometimes it's attached to the work table or further away on a structure, fabrication, or piece of equipment, but it is important to have a good clean ground. If the wire sputters at the beginning of the weld and the arc seems like it doesn't want to start, check the ground connection. Trim the wire 1/4 to 3/8 of an inch from the end of the contact tip. Get comfortable and use both hands on the wire feed gun so you can be as steady as possible. When you pull the trigger, circuits in the power source provide current to the wire and the drive rolls start to feed wire. When the wire touches the metal, the arc is started. The shape and amount of weld, along with penetration and weld fusion, are controlled by the distance the gun is held from the metal, the angle of the wire feed gun, the voltage and wire speed settings, and the travel speed. During the weld, you have to focus on the molten puddle, constantly analyzing how fluid it is, how the edges are flowing out, and watching the weld build up. Even though the welding machine does automatically maintain the arc length, the amount of wire that sticks out from the end of the contact tip to the metal, called electrode extension or wire stick out, will affect the amount of heat at the weld. CV power sources try to maintain a constant voltage, then provide the amperage necessary to burn off the wire. Longer electrode extensions allow the wire to preheat, reducing the amperage necessary to burn it off and reducing the heat at the weld. Shorter electrode extensions cause the amperage and heat to increase. Depending on the specific wire and wire diameter, the recommended electrode extension can range from 1/2 inch to 2.5 inches. For the smaller E71T11 self-shielded wire we're using, the wire stick out from the contact tip to the metal should be around 1/2 to 1 inch. For a smooth weld bead, you want to maintain a consistent wire stick out. While you want to avoid holding the gun closer, which can agitate the puddle, one of the unique characteristics of the self-shielded flux core wires is that you can back the gun away to fill gaps in poorly fit joints. You need to watch the puddle though, keeping it hot enough so the molten metal flows out on the sides. Under normal welding conditions, the gun can be held anywhere from nearly perpendicular to around a 15-degree angle back towards the weld. This is referred to as pulling the weld. When the gun is held more perpendicular, the arc stream is directed right onto the metal, causing the puddle to form and spread quickly. This can be used with a faster travel speed to limit penetration on thinner metal or for making smaller weld beads. As the gun is angled back towards the weld, some of the heat is taken off the metal. This allows a slower travel speed to build up more weld without overheating the base metal. You do want to avoid angling the gun too much. All the heat will be directed back onto the puddle, limiting penetration and possibly overheating the molten filler metal. Whether you're holding the gun up to spread the puddle or angling it to build weld, try to maintain a consistent gun angle for a smooth weld bead. For most welds, you can just move the gun in a straight line. A consistent wire stick out and travel speed will produce a uniform weld. You can also use a slight side-to-side motion, watching the outside edges to make sure the puddle is flowing out. As you gain experience, you can use more gun movement to deposit more metal, but avoid big wide gun movements that make the puddle more fluid and difficult to control. Either running straight or using a little gun movement, you want the wire and the arc directed at the leading edge of the molten puddle. This not only helps ensure good penetration and weld fusion, it keeps the molten slag back over the weld. This is very subtle, but where the wire hits the puddle makes a huge difference. If the wire is directed back further, the weld buildup limits the amount of heat that's transferred to the base metal, reducing penetration. Also, pushing the puddle in front of the wire increases the chances of trapping slag under the weld bead. Try to keep the wire towards the leading edge of the puddle, using the gun angle and direction of travel to keep the molten filler metal and slag behind the wire. The voltage and wire speed settings are the main control of the potential amount of heat and size of the weld. There are two parts to making the final adjustment. First, for penetration and weld fusion, the arc has to produce enough heat to melt the base metal while the filler wire is continuously added to the molten puddle. When the voltage and wire speed are set too low, the base metal does not get hot enough to melt, so the filler metal just stacks up on top. As the voltage and wire speed are increased, a molten pool forms, flowing out to the sides. The filler metal is fusing to the base metal, the weld is starting to penetrate, and you have control of the edges of the puddle. Increasing the voltage and wire speed spreads the molten puddle. The filler metal becomes more fluid and produces a smoother finished weld bead. Eventually, the puddle and base metal become too hot, making the weld buildup extremely fluid. This range from the point where the puddle is formed to the point where the filler metal is overheated is referred to as parameters. Typically, voltage and wire speed parameters are fairly wide, leaving the final settings up to the individual welder depending on metal thickness, weld position, and the level of skill. Once the amount of heat and weld deposit is determined, the second part of adjusting the voltage and wire speed is tuning the arc length to provide a stable transfer of filler metal into the molten puddle. This adjustment can be made on some practice metal, adjusting either the voltage or the wire speed, as long as the dial is a rheostat and infinitely adjustable. If the dial clicks into ranges, you cannot change it during the weld. Watch the tip of the wire, looking directly at the arc length. If the wire speed is too fast for the voltage, the wire will run into the puddle, kind of exploding and causing excessive weld spatter. If the wire speed is too slow, the arc length is increased, causing the puddle to widen and flattening the weld buildup. The voltage and wire speed should be tuned for a short arc length, right above the surface of the metal. Experiment with the voltage and wire speed. Watch the arc length, the puddle, and examine the finished weld bead. Most welding machines provide a chart with recommended settings. As your welder skills improve, you can increase the voltage and wire speed for higher deposit rates, better penetration, and smoother weld beads. The travel speed, how fast you move the gun, also affects the amount of heat at the weld. If the travel speed is too fast, the metal doesn't have time to heat up. The weld bead will stack up on top with limited penetration and weld fusion. Traveling too slow will generally put the wire and the arc on the weld buildup, causing excessive filler metal deposit and making the puddle difficult to control. Watch the puddle. You need to travel slow enough to allow the molten pool to spread, and at the same time, fast enough to keep the filler metal from becoming excessive and overheating. Then maintain a travel speed that keeps the molten puddle the same size. That's about all there is to the fundamentals of welding with self-shielded flux core wires. Set the equipment up with the correct polarity. Have a good clean ground. Use both hands on the wire feed gun. Adjust the voltage and wire speed to allow the molten pool to spread out and tune for a short arc length. Maintain the recommended wire extension with the wire directed towards the front of the puddle. Use the gun angle and travel speed to control the amount of weld deposit. Then travel at a speed that maintains a uniform weld puddle. So far, all the demonstrations have been in the flat position. For a horizontal, we'll be welding across. Angle the gun up a little and slightly back towards the weld bead. Watch the top side of the puddle